Okay, here we go. I think we're recording, and Hannah and Rachel are here. What we're going to do is go to page 88 in the 10.5 note packet, and then there's a new note packet for 10.6 that I'll email to you guys. What we were doing here is talking about proving familiar theorems, but with a new technique. That is, using transformations instead of the old-style congruence theorems, basically. So let's prove angle, side, angle. We are given two triangles. Let's label them A, B, and C, and the corresponding vertices are D, E, and F in this order. And we're given that the angle at A matches the angle at D, that the angle at B matches the angle at E, and then the sides in between are congruent. And we're supposed to show that these two triangles are congruent. So I've started typing the proof, information-based proof. So let's let T be an isometry. So on a picture, we might draw it as, here's a function that moves the triangle on the left to the triangle on the right. And what I've done is map the two vertices that I know the angles congruence to their corresponding vertices over here. So last time we talked about our ability to map a triangle onto a congruent triangle, but I don't know that these two triangles are congruent yet. So I can't just say that T slaps this triangle on top of this triangle. That's what I'm trying to show. What I can say is I can find a transformation that punches A to D and punches B to E, and then I don't know where C goes. We want to show that it actually can go to F, but we don't know that yet. So let's call C prime wherever C goes. And there are two cases. One is that C prime is on the same side of line L. Line L is right here. And C prime, by the way, is not on line L because C wasn't on segment AB over here. So C prime either goes to the left of L or to the right of L. Case one, it goes to the right of L. So maybe C prime is out here somewhere. And then let's join E and C prime and D and C prime. And what I'll try to show here is, in fact, this situation can't really happen. Or what I mean is that, in fact, the red triangle actually has to be the black one. The C prime really has to be point F. So we know that isometries take a triangle to a congruent triangle. So if T takes this triangle to the red congruent triangle, then DEC prime really is congruent to ABC, and now I'm trying to show that DEC prime is really DEF. Since isometries preserve angles, I know some other things. I know that angle C prime DE is congruent to angle CAB. Why is that? Because that's exactly where the transformation sent it. It took A to D, and it took C to C prime. So the angle in between here is preserved. And you should already start being suspicious, right? How can the black angle and the red angle both be congruent to this? Well, the answer is it's going to be the same angle. That's how the proof is going to work. So the CAB, we know we were given, is congruent to FDE. So we know that C prime DE and FDE are the same angle, which tells us that C prime is on line DF. That's the protractor postulate, I guess. If these two angles really are the same, then this point C prime actually has to be on line DF. But then let's play the same game at angle B. So we know that angle C prime ED, C prime ED is the same thing as angle CBA, because the transformation takes an angle to a congruent angle. And CBA was given to be congruent to FED. So if C prime ED and FED are both congruent to the same angle, they're congruent to each other. And this tells us that C prime, in fact, is on line EF. Well, the pinchers are squeezing together. I know that C prime is on both of these two lines. In other words, those two lines intersect at C prime. But I also know another point on both of these two lines, right? F specifically. So if the two lines intersect at C prime and the two lines intersect at F, the only choice is that C prime and F have to be the same point. So two lines can intersect at most once. So point C prime equals F. And then we have that triangle ABC is congruent to triangle DEF, which was what we were supposed to show. Yeah, it's really, it's not hard and it's not long. It's just another way of thinking. Always the transformation comes first, and then you talk about the consequences of it. Okay, what I did here was to send A to point D where I wanted it to go, and send B to point E where I wanted it to go, and then lived with where C went. It might go on the right side of the line, correct? On the same side as F. It might go to the opposite side. So what happens then? Then the picture is like this. Here's still A, B, C, and D, E, F, and we still have congruence here and here, here, and this side. But now the new triangle is over here. Here is point C prime. And T took triangle ABC to this new blue triangle. But T is an isometry, and isometries preserve angles. So in fact, the angle at A is congruent to angle EDC prime, and the angle at B is congruent to this guy up here. And so do you see a reflection sitting there waiting to happen? I'm trying to get to the right-hand triangle, and if I reflect the blue triangle across line L, it goes there. So how can we officially write that down? Let's label this line L again, and let's let so letter U be the following transformation. First, it's T, so that would take triangle ABC to the blue triangle. But then when I finish with that, I'm going to reflect it across line L. And so when I do both of these things in that order, the original ABC triangle goes to the blue triangle, gets flipped across to triangle DEF. And if I let C prime be U of C, C double prime, say, be U of C, it's going to end up over here. The claim is that C prime equals F, and basically it is by part 1. I don't think I'll go through all of the detail again, but you know what reflections do. They preserve angles as well. This triangle really is, because of the way it's set up, it's going to flip exactly to a congruent triangle on the right. And if blue left and black right are congruent, point C prime is going to land right on top of C double prime. And again, this transformation takes the one to the takes ABC to DEF, and so the two are congruent. I guess the advantage of being in class is you get a chance to ask questions. Anything more to say about that? All right. So I already mentioned this, I think, but regarding topics in here, I think if we can get through 10.6, and in the rest of this video, we'll probably mostly do that, then the world won't end if we don't go to 10.7, so we'll get through 10.6. 10.6 will seem hopefully pretty familiar, because it basically does the same thing as what we've been doing so far, except involving similar triangles instead of congruence triangles. All this discussion about isometries gave us different ways of thinking about congruent triangles and congruence theorems. And so now this material is going to give us different ways of thinking about similar triangles and similarity theorems. Let's start with the idea of a dilation. I'm sure you've seen this before in some material on proportionality. So what is it officially? If I define a dilation, I start with a fixed point in the plane and a positive real number. And then the dilation is of the plane. So it takes every point in the plane and sends it to some point in the plane. It doesn't move the origin. So this point O is a fixed point of the dilation. Every other point does get moved, and it gets moved along the ray. So point A gets moved to point A prime. It stays on the ray from the origin, and it gets moved so that the new distance is k times the old distance. So on my picture here, it looks like the distance from O to A prime is maybe 3/2 the distance from O to A. I'm just guessing, but that's the basic idea. So here, OA prime would be about 3/2 times OA, and OB prime would be about 3/2 times OB. And the point is the 3/2 is exactly the same number. And OC prime is 3/2 OC, and so on. And not just for this triangle, every point is getting moved. So if I went out to the left of point O, these jobbies are all getting moved 3/2 away from the origin along the same ray. It's like the whole world is expanding around the origin. So K, the proportion factor, needs to be a positive number, but nobody said that it had to be greater than 1. So I could talk about the dilation around point O, and with a dilation factor of 1/2. And what would that look like? What would triangle ABC end up looking like? Point O is going to stay fixed, and every other point moves along its ray between itself and the origin. So a good way to start out would be to draw some guidelines between the origin and each of the 3 vertices. And now the proportion factor is 1/2. So everybody moves to distance 1/2 of what it was from the origin. So point A moves to A prime about there, and B moves to B prime about there, and C moves about there. And so the net effect is my triangle ends up about like this. I'm off just a little bit. And you might already starting to be suspicious of something. These triangles look very much alike. They're not the same size, but they look like they may have the same shape. And so the idea of similarity should be starting to bubble in our minds. Before we decide that for sure, let's answer a couple of other questions. We define functions like this, but is a dilation really a transformation? That meant a function that was 1-to-1 and onto. So if, for example, I was checking 1-to-1, I would say, all right, here's my origin. I want to know if, and the check for one of the ways to check for 1-to-1 is if the inputs are different, do the outputs have to be different? In other words, if I choose point A and point B and dilate them, does it have to be the case that the dilated points are also different from each other? And it sure seems like it. If I run helper guidelines through these points, then just to be definite, let's suppose the dilation factor or scale factor is 2. Then A prime is going to be out here somewhere. And B prime is going to be out here somewhere. And do those have to be different points? Yeah. They started out being on different rays, and so they have to end up on different rays. Or there's another case that I should think about. What if A and B really were on the same ray, collinear with O? Well, then if they were different points, they'd have to be different distances from point O. They might be on the same ray, like If I started with B and B prime, for example, they'd be on the same ray, but when I dilated them, because their starting distances were different from O, their finishing differences would be as well, and they'd still be different points. So this is 1-to-1, and it turns out by pretty easy to show as well that it is also onto. So dilations are transformations, yes. So now we know about all the isometries that we discovered, rotations, reflections, translations, glide reflections, and now dilations are another kind of transformation. Are they isometries? Is a dilation an isometry? An isometry means a transformation that preserves distance. And it sure doesn't look like it. If I look back at my triangle pictures, any of the two triangles we did above, those are not distance preserving transformations. So no, in general. There is one case, though, when it is. If I have a scale factor bigger than 1, I change sizes. I make them bigger. If I have a scale factor less than 1, I change sizes. I make them smaller. If I have a scale factor exactly equal to 1, then nothing happens. So the answer to the question is really yes, but only when k equals 1. And to dilate by 1 is to do absolutely nothing. It's a very boring transformation. Everybody just stays where they are. So generally, dilations are not going to be isometries. Okay, let's push this a little more. On the diagram, let's call the center O as before. And now if I actually did this really carefully using surveying equipment, I would say something like this. Here is a case when the dilation being applied is at point O and the scale factor is exactly 2. So E is twice the distance from O, or let's say it this way, OE is 2 times OB, and OD is 2 times OA, and so on. So I see those distances between points and the origin doubling, but I see other distances. In fact, I see all distances doubling. AB is doubling from 6 to 12, and BC is doubling from 4 to 8, and so on. Nobody said that had to happen. The dilation itself just said the distance of every point from the origin was doubling, but it turns out that all distances like this double. And so that's what this theorem is saying. For any dilation with scale factor k, no matter which pair of points I pick, their new places, their images, are k times as far apart as their old places. Let's prove this. It's pretty short. By definition, what about OA prime and OA? I looked at this ratio. And A prime and D, I mean, to be the same thing here. Let's label that. D is A prime and E is B prime. By definition of dilation, the new guy, OA prime, the new distance OA prime, is twice the distance of the old, or here I'm doing a general proof, so it's K times the old distance. And that same thing would happen if I worked with point B as well. So OB prime divided by OB is also equal to K, that same number. And so now if I just draw the essentials of what I have, here's point O, here were points A and B, and A prime and B prime. And if I join these guys like this, I'm trying to talk about what happens to distance AB. But there are two triangles here. One is the big one, and the other is this small one, OAB. And we don't know that these guys, like AB and AB prime, are parallel necessarily. They do turn out to be that, but we have enough information. The angle at O is common to both the big blue and the small red triangle, and we know proportionality of pairs of sides like this. So from a while back, remember we have something side angle side similarity. We can say that triangle AOB is similar to triangle A prime OB prime. But if two triangles are similar, then all three pairs of sides have the same ratio. So then by the, let's see, we called it the main similarity theorem, the similarity theorem. And the third pair of sides is A prime B prime is to AB. That also needs to be the same constant as the ratio of the other sides, K. And that does it. I clear fractions here in this last equality. A prime B prime turns out to be this fixed multiple. So what we've discovered is that a dilation, in fact, changes the distance between any pair of points by exactly this factor K. Not just point to origin, but point to point, everywhere in the plane, point to point. And you can think about a dilation again, just it's like rings around the circle, and everything is just expanding outward in all directions if K is greater than 1, or they're crunching inward around the origin if K is between 0 and 1. All right, so let's now work with this business. What about when we have the situation where every pair of points is moving by the same factor? Let's call that a similarity transformation. If it's a transformation so that the images of each pair of points is K times the distance between the points themselves, we will call that a similarity transformation. And then here is a list of properties that should look pretty familiar. I literally cut and pasted in my word processor. We had basically these same properties before for isometries. You look back 8 or 10 pages in our notes, and there they were. So some of them are direct copies. This idea that a similarity transformation preserves collinearity between lines, angles, and so on. That's exactly the case for isometries. And then there were some properties that involved distance. And in the case of isometry, it was always one distance equals another distance. Now, not so, but you can predict what's happening. The image of a segment under a transformation is a segment, and it's K times as long, as distances are growing by K times. Triangles are not going to congruent triangles anymore, but they're going to similar triangles. Circles are going to circles, but not of the same radius anymore. The radius gets expanded or contracted by this factor of K. and regions get sent to regions, and the area gets adjusted, not by a factor of k, but by a factor of k squared, right? If you take a rectangle and you double the lengths of all its sides, the area gets multiplied by 4 rather than by 2. So far, so good. Okay, here's another place that I cut and pasted. We talked before about when you had two isometries and you did them back to back. You did one and then the other. The net effect is an isometry. When you have two similarities and you do one and then the next one, the net result is a similarity. And in fact, the proportionality constants follow along and multiply. So if you scale everything by a factor of 2 and then scale everything by a factor of 3, the net effect is you've scaled everything by a factor of 6. So when I put similarities together, I just get another similarity. And so the same question comes up as we had for isometries. If I do a whole bunch of isometries and then in the end ask, what was the easiest way to get from my starting point to my finish point? If I did like 3 reflections and 4 rotations and 2 glide reflections and a translation, the net effect is, we had a theorem that said that whole thing is going to be either a rotation, a translation, a reflection, or a glide reflection, just one isometry. What about for similarities? If I do 17 different similarities, what's the most complicated thing that I could end up with? Is it just one similarity, or might it be 2 or 3 similarities that I could boil it all down to? So let's tackle that question. Our first shot at it, and it's the bulk of the work, is to say that every similarity is at most 2 transformations, one isometry and one dilation. By the way, let's go back and talk about how, let's go back, draw a picture here. How does a dilation compare with a similarity transformation? Is every dilation a similarity transformation? On this theorem at the top of page 90, we in fact showed that. I started with a dilation and showed that every pair of points is getting scaled by this k factor, and then we defined transformations that do that as similarity transformations. So this definition and this theorem put together show that every dilation, yes, is a similarity transformation. So right here, I'm going to draw a Venn diagram. The big circle is all similarity transformations. And then inside here are dilations. And the question is, are these really the same blobs, or are there similarity transformations that are not dilations? Are they the same thing, or is similarity really a special case of, is a dilation really a special case of a similarity transformation? So the theorem says special case. Not every similarity is just a dilation, but every similarity is at most an isometry combined with a dilation. One isometry combined with one dilation. So if I do 17 different similarities back to back to back, the net effect is at most dilate and do a rigid motion in isometry. Let's show how that works, or do I want to do a proof? I think I'll go on to the demonstration proof at the end, and then we'll come back in our last 15-minute segment and go through why that previous theorem is true. So let's use the idea of similarity to prove this. I think maybe you did this exact problem for homework, if not something very similar to this. I start with triangle ABC, and I find the midpoints of two of the sides and call them DE and join those with a segment. And we're trying to prove then that DE is parallel to BC and that it's of 1/2 the length. So let's write down what I just said, that we are given triangle ABC. So let D and E be the midpoints of segments AB and AC. Now, this is going to be a transformation-based proof, and we're talking about similarities. So I think I want a similarity that somehow relates two pieces of this picture. And as far as similarities go, I mean, I could think about abstract similarities, but the ones we specifically talked about are dilations. So I would like to dilate something from one of these figures to another. So specifically, there are two triangles in this picture, ADE and ABC prime, and they sure look a lot alike. So let's take a similarity transformation specifically to be a dilation. And where are we going to dilate from? It does matter. I think I'm going to go up here to vertex A and dilate so that it blows point D down to B and E down to C. So we'll dilate from point A. By what factor? Well, D is the midpoint. So AB is twice the distance of AD. So let's dilate by a factor of 2, or I think to make the proof work out, I'm going to go the other direction and make it be a factor of 1/2. So this be a similarity transformation. We know that dilations are similarity transforms. And then what happens to triangle ABC under this dilation? A is the origin or the center point, so A doesn't move. Center of a dilation doesn't move, and then everybody else is going to get sucked down half its distance, and so triangle ABC, sure enough, is going to get dilated down exactly to triangle ADE. But we know that similarity transformations take triangles to similar triangles. So if this guy, ABC, mapped onto ADE, these two triangles are similar by definition, basically. Not maybe definition, but theorem on page 90, part 2, that triangles get sent to similar triangles. So triangle ADE is similar to triangle ABC. And the scale factor is 1/2. So just from what it means to be similar with a given scale factor, the fact that DE is 1/2 of BC is exactly what it means to dilate. Distances get halved. And the fact that these two triangles are similar means that we get congruent angles here. So in particular, angle ADE is going to be congruent to angle ABC. Two triangles are similar. But now, what are we trying to do? Show that DE and BC are parallel, and now I have corresponding congruent angles, so I could get corresponding alternate interior angles if I wanted to go through that. Anyway, basically the alternate interior angle theorem finishes it off for us. So finally, DE is parallel to line BC by, I'll just say, alternate interior angle theorem. And I don't know if you remember doing this problem. I'm not sure if you did, but if you remember doing this problem, it's pretty much the same idea, actually. The fastest way is to show similarity here. And using similarity transformations is a very natural way to make that happen or show why it happens. Any questions, comments about that? All right, let's stop there. We'll go back and finish that one proof and talk a little bit about the final exam on Monday. I guess we're going to meet.